Welcome to The Explainer. Today, we are going to get under the hood of technology. We're going to break down the core principles that separate that frustrating, laggy software from the amazing, super fast apps you actually love to use.
So, let's kick things off with a puzzle. It's a real head-scratcher that seems to completely defy logic, but it actually gets to the very heart of what makes good software tick. Here it is. How can a slow, old computer absolutely smoke a brand new, top-of-the-line machine doing the exact same task? So here's how we're going to tackle that. We'll start with the problem itself, that software slowdown. Then we'll look at three key parts of the solution, thinking in terms of efficient recipes, organized data, and reusable blueprints. And finally, we'll connect all this theory back to the actual tools developers use and, why any of this really matters.
Okay, so let's talk about the problem. We've all been there, right? You're trying to do something important, and your app just freezes, or a website takes forever to load. Your first instinct is probably to blame your phone or your computer. But what if I told you the real problem is often hiding deep inside the code?
All right, to really see what I mean, let's imagine a little showdown. In one corner, we've got computer A. It's brand new, state-of-the-art, super fast. In the other corner, computer B. It's a lot slower. Now, if we give them a small job, like searching a short list, the results are exactly what you'd expect. Computer A just blazes through it. It's not even a contest.
But here's the thing. What happens when we scale this up? When we stop giving them these tiny little jobs and throw a real-world challenge at them with a massive amount of data? Well, as that list gets bigger, something absolutely wild starts to happen. That pokey little computer B, it doesn't just catch up. It actually starts to pull ahead. And look at this. When the list gets truly enormous, the difference is just staggering. Our super fast computer A would literally take an entire year to finish the job. Computer B, it gets it done in just over a millisecond. So what in the world is going on here? How is that even possible?
The secret to computer B's incredible win isn't about its hardware at all. It's about its method. And that brings us to our very first key concept, algorithms. So if you look at the formal definition, an algorithm is just a step-by-step procedure. It's a set of instructions that tells the computer exactly what to do and in what order to get from a problem to an answer. But honestly, a much better way to think about it is as a recipe. In that showdown we just saw, the super-fast computer had a really bad recipe. The slow computer, on the other hand, had a brilliant one. See, the intelligence of the instructions matters way more than the raw power of the oven. And this right here is the heart of it. Computer A was using what's called a linear search. That's like looking for a name in a phone book by starting at the very first page and reading every single name until you find the one you're looking for. It's brute force. Computer B, though, used a binary search. It was much smarter. It jumped straight to the middle of the book, saw if the name was in the first half or the second half, and bam, instantly threw away 50% of the book. It just keeps doing that, and it finds the name exponentially faster. It's not about working harder, it's about working smarter. That's a good algorithm. Okay, so having a great recipe, a great algorithm, is absolutely crucial. But an amazing recipe is only half the battle, right? You also have to be able to find all your ingredients quickly. And that's where data structures come in. A data structure is just a specific, intentional way of arranging your data in the computer's memory so you can get to it and use it when you need it efficiently. Let's go back to our analogy. If the algorithm is the recipe, then the data structure is your pantry. Think about it. If your pantry is a total mess, even the best, simplest recipe becomes a slow, frustrating nightmare to follow. But a well-organized one, it makes everything smooth and fast. And you've got lots of options for organizing that pantry. You could use an array, which is basically just a simple numbered list. Or maybe a stack, where the last thing you put in is the first thing you take out. Just like a stack of plates. Or you could use a queue, where the first one in is the first one out, exactly like waiting in line at the store. The key is picking the right structure for the job you're trying to do. All right, so we've got our efficient recipe. That's the algorithm. And we have our well-organized ingredients. That's our data structure. Now, let's zoom out. We're not just making one dish anymore. We're designing the entire kitchen. And this is where software design patterns come in. Now, these aren't actual pieces of code. Think of them more like a template or a formalized best practice that programmers can use to solve common problems that pop up over and over and over again. The perfect analogy is an architectural blueprint. When an architect designs a house, they don't have to reinvent the idea of a door or a staircase or a window from scratch every single time, right? Of course not. They use proven, effective blueprints for these common challenges. Design patterns are the exact same thing, but for software.
And these blueprints tend to fall into three main buckets. You've got creational patterns, which are all about the best ways to create objects. Then there are structural patterns, which focus on how to assemble all your different pieces into larger, more useful structures. And finally, behavioral patterns are all about making sure those different parts can communicate and work together effectively.
Okay, so that's a lot of theory. We've covered algorithms, data structures, and design patterns. So the big question is, how do these ideas actually connect to the real-world tools that developers are using every single day? Well, it's pretty straightforward. Developers use programming languages like Python to write out the actual instructions for their recipes, their algorithms. They use databases and languages like SQL to build and manage their pantries. Those are the data structures. And they use version control systems like Git to manage their blueprints, which lets them track every change and collaborate on the overall design. All right, so we've gone through all of this, from algorithms to data structures to design patterns. What is the one crucial thing you should take away from all this? The big takeaway is this. Building great software has almost nothing to do with just having powerful hardware. It's an act of intentional design. It's about consciously choosing the right recipe, carefully organizing your ingredients, and following a solid, proven blueprint. I mean, think about an app like Google Maps. It's not fast just because you have a new phone. It's fast because it uses absolutely brilliant algorithms to find the best route, super efficient data structures to manage a mind-boggling amount of map data, and it's all built on top of solid, proven design patterns.
So this really gives us a whole new lens to look at technology through. The next time an app on your phone starts to lag or just completely freezes up, don't just blame the phone. Ask yourself a different question. Was it a problem with just one line of code? Or was there a much deeper flaw in the recipe, the pantry, or the blueprint itself?